Let's please take a real world example here to walk you through what I have explained theoretically. So the problem asks you here to design a water pump impeller and it gave you the design flow rate of 1200 gallon per minute, and it gives you the head as 450 feet, as well as rotating speed. So with this information, so basically you get this information from the customer, and based on this information you proceed with the design of a pump, and you should actually select everything, like select the type of the impeller. Is it radial, is it mixed, is it axial? So you do everything from these three parameters only. So the step A to solve this problem, start with this calculation of specific speed. We have calculated the specific speed like N times flow rate, and then the flow rate is in gallon per minute, and then head is in feet. So we have calculated the dimension of specific speed and found it to be around 850. So you go to the chart, figure 420, and from figure 420 you take the flow rate. So you take the flow rate here, and so you take the flow rate and the dimensional specific speed. You take them to the figure, and you will find that the intersection of these 2 points will give you what the efficiency. Okay, so in our case here, with a specific speed of 851 and a flow rate of 1000 or 1200 gallon per minute, the overall efficiency of this pump should be around 76%. Okay, then from here we calculate the shaft power. The shaft power is nothing but the hydraulic power, Q times delta B, over the overall efficiency. So from this we already determined the overall efficiency from figure 420, and we have calculated the hydraulic efficiency is nothing but the pressure, and the pressure of course can be determined from the head times the flow rate. So the pressure here 450, how did we obtain it? 450 times the specific weight will give you the pressure. Okay, and then this will give you how much, like for example this specific weight of water in English unit 62.4, and the 1200 is the flow rate, and this is a conversion factor. Okay, so this is a conversion factor, and the overall efficiency is here. So you get the shaft power as around 99,000 feet-pound force per second. From figure 4.2, we can say that the safest assumption to make here is to choose a radial impeller. Why? Because the specific speed is less than 1000, and we have a flow rate of 1200, so we are in this zone pretty much. Okay, so we are in this zone pretty much. We're not even, like, we did not even reach here, so we are in the zone. We are in this zone. Okay, we should select either one of these two impeller types. So we'll go with we will say that radial impeller is appropriate for this application. And since so up to this point we have officially selected the impeller type, and then from the impeller type, of course, we go ahead and find the diameter of the shaft, right? The diameter of the shaft is this much, and the torque is B like shaft power over omega, and then from here the maximum allowable shear stress should be given. So I should have gave you the maximum allowable shear stress because it's different for each material, and this should be known. But for 300, in this particular example, the shaft of the pump is made from stainless steel 316. So the maximum allowable shear stress for this shaft is around 10,000 pounds per square inch, and with a safety factor of 1.5, we will say that, by the way, this is a purely radial impeller. That means the inlet configuration should match the hub of the diameter, the diameter of the hub, as well as the diameter of the tip. There is no angle like what we have seen with a mixed flow in the previous slide. For example, in mixed flow we have an inclined lead, the leading edge of the plate is inclined this way, but in this case we have a horizontal, we have a horizontal leading edge. Okay, that's why the diameter of the tip is equal to diameter of the hub equal to diameter 1. Figure, yeah, just go back and see figure 419. It will show you what do we mean here by d sub t1 equal to d sub h1 equal to d sub 1. So from this information we actually proceed with the determination of the rotor speed at the leading edge, as well as the volumetric flow rate. And then I have told you that in order to avoid boundary layer, in order to avoid separation of the flow, we make the flow velocity at the leading edge a little bit greater than the absolute flow velocity at the eye of the impeller, and it's taken as 10% more than the eye absolute velocity. And the flow area is by d1b1 or 2 by r1b1, but it's multiplied by contraction factor here to account for the losses that occur in the intersection. So we have selected, remember I have told you that you have to make the eye flow coefficient between 0.25 and 0.30. So in this case we have selected the eye flow coefficient to be 27%, and then from this selection what we can say, okay, this is the eye flow coefficient selected. And remember, we know the omega, right? We know the flow rate. So from this you can easily determine how much of eye radius for this impeller you will need, and of course based on that you can find the diameter of the hub, and the final results is that you will be able to calculate the absolute flow velocity at the eye, and then the as you can see here, the flow velocity at the inlet of the leading edge, and the flow area at the inlet of the leading edge, and then the plate height at the inlet with a contraction factor. So it is indeed so, and this beta plate 1 has been selected to be 17. As I have told you before, the difference between the beta plate at the leading edge and the relative flow angle at the leading edge should be like around 2 to 3. So here it's around 2.4, which is a great assumption. So once you know the beta plate 1, you can easily determine the beta plate 1 or vice versa. Okay, and from the beta plate 1 we can of course determine the absolute relative flow velocity at the leading edge. Okay, so we continue, and then we'll then see here pertains to the outlet configuration or the outlet size of the pump. So with the non-dimensional, this is the non-dimensional specific speed. Okay, with this number we have calculated this number and found it to be around 31.1%. And from the corridor diagram, so you go to the corridor diagram, which is the figure there, and you go to point 3, for example, you go to point 3 in the coordinate diagram, and you read how much will be the specific, the non-dimensional specific diameter, delta sub s. Okay, so you go there and find how much delta s is there. Once you find it, you can of course determine d2. So d2 you will get it from this formula, and then from d2 you will calculate the rotor speed at the exit, and from the rotor speed at the exit we proceed to compute the flow area. But before proceeding with the computation of flow area at the exit, we need to calculate, for example, the hydraulic efficiency, the slip factor. Okay, so the hydraulic efficiency, I'm serious, this is the hydraulic efficiency, slip factor. So the slip factor is this much. It's function of the blade number, beta blade. Okay, so the hydraulic efficiency is only a function of the volumetric flow rate. You calculate that, and from there you find the tangential flow velocity at the exit, and you find the radial flow velocity at the exit. So which is not appropriate. So the diffusion factor have been calculated and found to be greater than, because yes, the main point here of actually calculating W1, W2 is to determine if the diffusion factor is between the normal range, which is in this case, since it's greater than 1, it's not appropriate, and a different diameter at the exit of the rotor has to be selected. So we have right now selected a different outlet diameter of this impeller and made it to be equal to 15 inch. So based on this new diameter, the U sub 2, the rotor speed at the trailing edge of the impeller will become this much, and you proceed with the calculations until you make sure that the diffusion factor, this factor is less than 1 but greater than 0.7. Once this condition is satisfied, then you say, okay, here is the dimensions and the details of the pump. The blade profile, and I have showed it to you in the previous slides how to get it, but the blade profile can be proven to be, it is function of the radius, and it is actually following this formula. Here is the thing. So this beta blade represents a blade angle from the inlet all the way to the outlet. So that means if you are at the inlet, then beta blade 2 is equal to beta blade 1, and then this term will equal to 0, which will make the entire term equal to 0. And this is this is when you are at the leading edge. But if for example, if you are at the leading edge, then beta blade 2 is different than beta blade 1, and this will result in the angle of the blade being different from the inlet. So I mean this would result in the blade angle being different between the inlet and outlet. So, and the table here shows what is the distribution of the table shows the distribution of the blade angle from the inlet, from R1. So basically this is R1 until all the way to R2. Okay, so you have R1, for example, at this point, and you have R2 at this point. So it shows you how the theta changes from R1 to R2. Okay, now is in degree, and I mean the unit of the angle plate is in degree, whereas the radius is in inches. Okay, and we have also shown that the change of the angle it can be expressed this way And here we just saying an example that if we have selected 0.43 inches, then beta plate, delta theta, delta L, as well as L can be tabulated as follows. So you choose a segment each time. Delta here delta R represents the segment. So if you, for example, let me show something. So from 3.2 to 3.63, the segment here is how much the difference? So how much the difference between the first two? So 3.63 minus 3.2. The difference is how much? 0.43, which is this much. Okay. So every time you increase 0.43 and find what the blade angle at this location. So you find it first, let me see, at this location, and then you first at this location, all the way to R2. Okay, this is basically 3.2, and this one is 7.5. Okay, and this increment, this little increment, is 0.43. So just be careful about that. And then the table shows that beta plate 2 is equal to how much? We get it from here. Okay. What is the beta plate 2 means we are at the exit here. So at this point. So the beta plate 2 at this point is how much? Is 27.5. And the 17 is here. Okay. It was assumed, I think. With that being said, the length can be calculated. Remember, the length is delta R square, okay, plus R delta theta, right? So please check this equation as well. So all square under the square root. So you sum all of these. So you sum delta L here, delta L. So basically here L is delta L plus delta L here, or 1.4, and then you add this much, you add to the 1.471, you add to it 1.422, and then you add this is the delta L. Okay, just be careful of that when you work a problem like this. And example 4.8 is a continuation of example 4.7, but we wanna in this example continue and design the volute of the pump. In example 4.7 we have the flow rate, we have the head, and the specific speed is this much. So from that we have calculated the specific speed to be around 850. We calculated the diameter of the outlet configuration from the required head, and then the blade height, and then the rotor speed, and then beta plate 2. So all of that. So then from figure 4.24, from all of this information, we can get K3. Once we get K3, so we have obtained K3 as 0.47. So how did we get it? 0.46 is here, for example, 2468. So 246 is this much. This is because the specific speed is what? 850. So it depends on the specific speed, because in our case the specific speed is 850. Now this is around 0.9, right? So you have to make sure it's exactly at 0.85. At 0.85 at this point, so you go straight all the way to this point. And remember, this number should be multiplied by 1000 to represent the actual, because the scale here is divided by 1000. So in order to know which is which, you need to multiply the values of x-axis by 1000 to get the actual value. So the volute here, now it is saying that, so we have calculated K3, and from the head, we know the head, right? We can calculate how much of velocity would be at the exit of the volute, and then the area of the flow at the exit of the volute is this much, and then so we get rid of this. Also from this figure we have d3 minus d2 over d2 is this much. Okay, so we have to obtain all the information we need for the design aspect of a radial flow pump. So now it's saying if a trapezoid with an included angle of 30 degrees as shown is selected for the basic geometry, you follow this procedure. You are just required to know this information if you are having a trapezoid section of a volute. Okay, now it is, it's important to know all the aspects, but volute usually is complex to design and has many aspects, and many aspects need to be considered. With that being said, let's I give you exercise to work a problem that basically it's a design problem, and it's saying here design a water pump, so it's a design problem. Once it says design a water pump, that means it's a design problem, and it should involve selecting the impeller type, should involve sizing the inlet configuration of the pump, sizing the outlet configuration, doing the blade profile, and getting the mean the total length of the blade, or the total length of each blade, and then getting the volute and the user information. So it is pretty much similar to the example 4.7. So the procedure is pretty similar to that example. You can basically determine everything by first